Let's go over Newton's first law of motion. So think about ice hockey. If you hit a puck, it goes on its own across the ice. After the puck is hit, it slides across the ice with very little friction. Newton's first law of motion states that an object that rests or motion stays in rest or motion until compelled to change by net force. That's pretty obvious, and that's the joke. People can't figure out. People can't understand why Isaac Newton's a genius when he figured out that if we don't do anything, nothing will happen. So in the first law, the phrase net force is crucial. It's the vector sum of them all. So let's say that I'm going to use this later, so I'm not going to delete it. So let's say we have a box and we push it with 5 newtons, and we push back, and someone is pushing back with 2 newtons. We're still going forward at a net force of 3 newtons. And we don't care about the 2 and 5. We just calculate the resultant vector and calculate the force that way. So we're moving it with a force of 3 newtons. So that's why the net force is crucial, because even if we go back to that analogy, even if we apply another 2 Newton force, so 2 and then another 2 Newton force, that's 4, and the 5 Newton force here, we're going to have a 1 Newton to the east, regardless of this 2 Newton force that has been added to the right. So pretty self-explanatory and logical. It's the vector sum of them all. So a greater net force is required to change the velocity of some others. Push a train, it's not going to move. Push a coin and it will fly. Accordingly, we say that the train has more inertia than the coin. Inertia is the natural tendency of an object to remain at rest or at a constant velocity. And if you do force equals mass times acceleration, it makes sense, which is the second law actually, because it requires a greater force to accelerate something to the same effect with a greater mass. So in a seatbelt mechanism, there's something called a pendulum. So when you're speeding in this car and you have this seatbelt over you, let's say this is the pendulum right here, and it's over you. This seatbelt can move like forward and backwards, no matter what, because it's on this pendulum. So that's when you could stretch the seatbelt. However, when the car comes to a sudden halt, you note that your body is still accelerating because it takes greater force to slow your body down, because it takes a greater acceleration for your body to slow down. However, this barely weighs anything. It has less inertia, and therefore it will stop, locking the mechanism in place, and throwing the seatbelt over you. Pretty simple logic, pretty cool, and that's the logic behind the seatbelt mechanism. So, an inertial reference frame is a point of view where Newton's first law holds true. Key properties are that the frame itself is not speeding up, slowing down, or curving. It has constant velocity, and all Newton's laws work normally. A ball rolls by on a sidewalk. No one touches it, just rolls forward steadily with that same amount of force. Nothing is slowing it down. The sidewalk is the inertial frame. You're inside a car that suddenly speeds up. When the car accelerates, the ball looks like it rolls backwards towards you. But from the sidewalk, the ball is actually moving forward. So if we come back to this drawing, and when this car, so everyone's at rest here. When the car starts accelerating, what happens is that the car starts accelerating quicker than this ball can accelerate with it. So as a result, the car is accelerating or at a faster rate than this ball. So what will happen is that the ball will roll backwards. But technically, it's still moving forward as the car is moving forward as well. Because obviously, if the car is moving forward and the ball is inside the car, then the car and the ball will be moving forward. But to you, it looks like it's rolling backwards. And this is what's called a non-inertial reference frame. So that's 4.2. Pretty simple.